About 4.5 billion years ago, Earth was a molten planet covered with volcanoes and bombarded by asteroids. Volcanoes released huge amounts of steam, carbon dioxide, and nitrogen from the interior. Asteroids and comets carried ice and water-bearing minerals that vaporized on impact, adding more water vapor to the air. As the surface cooled, the vapor condensed into rain. Over long geological periods, that rain collected in low basins and formed the first oceans. These early seas were hot, acidic, and rich in dissolved iron and minerals from volcanic rocks, green or brown rather than blue, but they provided the conditions for the first microbial life. In those oceans lived simple microbes. Among them were cyanobacteria, which used sunlight, water, and carbon dioxide to make food by photosynthesis, releasing oxygen as a byproduct. The oxygen first reacted with the iron in seawater, forming iron oxide that settled on the seafloor. Over millions of years, this created banded iron formations, layered iron-rich rock that records the earliest oxygen production. Once the iron in the ocean was consumed, oxygen began to accumulate in the atmosphere. Most early microbes lived without oxygen. They were anaerobic, implying oxygen was poisonous to them. As oxygen spread, many of these organisms died, and entire microbial communities collapsed. This mass die-off is known as the oxygen catastrophe or the Great Oxidation Event, the first major extinction in Earth's history. Oxygen also altered the atmosphere's chemistry. Earlier, methane was abundant and kept Earth warm. Oxygen reacted with methane, producing carbon dioxide and water vapor that hold far less heat. Temperatures fell and ice sheets expanded. Some evidence suggests that Earth entered a snowball state, with oceans frozen at the surface for millions of years. Over a period of time, the volcanic activity and other natural processes increased greenhouse gases, which gradually warmed the Earth and melted the ice. After this event, oxygen did not disappear again. Photosynthetic microbes kept producing it, while other natural reactions consumed part of it, leading to a low but stable level of oxygen in the air, the first long-lasting oxygen-rich atmosphere in Earth's history. In the upper atmosphere, some oxygen formed ozone, which blocked harmful ultraviolet radiation and made the sky appear blue. Earth now had a more stable climate and an oxygenated atmosphere. Oxygen allowed organisms release far more energy from food through a process known as aerobic respiration, where oxygen helps break down nutrients completely. This extra energy made cells more complex, leading to the evolution of eukaryotic cells, cells with a nucleus and internal structures, and eventually multicellular organisms. The Great Oxidation Event thus marks the shift from simple microbes to a planet capable of complex life. Just like a phoenix, life on Earth was destroyed and reborn through the Great Oxidation Event, wiped out by its own creation, yet emerging stronger and more complex from the ashes.